All right, gentlemen, uh, we are in the first part of chapter 4, the higher order differential equations. In 4.1, preliminary theory, linear equations, we are learning all of this stuff, initial value and boundary value problems. What is it, their definition, and how should we determine these things? And homogeneous equations and non-homogeneous equations, we need to have some knowledge about these concepts. Then after learning this stuff in 4.2, we start solving differential equations. Okay. In the previous videos that I shared with you yesterday, it was about 4.1.2 homogeneous equations. And now, as I told you, I'm hoping that you have already watched and you have some idea. Otherwise, you may not understand when we use some terminologies or when we're solving equations. Okay. And also, I'm thinking to make a little bit change in our teaching methods, okay, teaching schedule. As you know, every Wednesday and Thursday we have 2 hours on Wednesday and 2 hours on Thursday. So actually, I do not see much active participation. I'm just talking here. You are listening maybe because of your internet connection. Maybe everything is clear for you. I don't know. Only sometimes some of you are asking questions. So I'm going to teach 1 hour without you and just upload this in YouTube. You can watch this, okay? But also, actually, I suggest you to watch this video during the scheduled time. For example, Wednesday you have class from 10 to 12. All right, 10 to 11. Maybe I'll share like 2 short videos. Each one is about maybe 15 minutes. Okay, you need to watch, and after that we should continue. Okay, if you don't watch this, you may have. If you do not watch this and if you do not study this from the book, then you may be in trouble. Trouble means when we talk about things here, you may not understand or it may not be clear for you. Okay, so in the last part of this subchapter, when we are actually using equation 6, equation 7, right? Actually, in scientific papers, every time writing something that is commonly or repeatedly used, it is not so practical. So now we are going to use this several times throughout this chapter. So you should understand when we say equation 6, we mean this. Okay, that is nth order linear differential equation. And also more than that, this one is homogeneous equation, right? Because on the right hand side, we have 0. That's a function of x, which is not multiplied by y, or it is derivative of any order, all right, is equal to 0. That's constant, okay? And this equation, we call this non-homogeneous equation. Why? Because here we have a function of x, and which is like, it looks like a constant term. Of course, it's not constant, it's a function, but it's not multiplied by y or the derivative of y or derivative of y of any order. Okay, this is non-homogeneous equation, nth order, because the function is differentiated n times, right? That's why we call this nth order. And non-homogeneous because here we do not have 0. We have a function. But here we have 0, and that's why it is called homogeneous equation. Okay, equation 6, we mean this. Equation 7, we mean this. Because now here we are going to talk about the solution of this equation, non-homogeneous equation. In the previous video, actually, we talked about homogeneous equation. Okay, so actually, you need to have some idea how actually not solving what we mean by the solution and how many solutions does it have, because if you solve this, the order is n, we get n fundamental solutions, and all linear combinations of these fundamental solutions, it gives us the general solution of this equation. Because in solving this non-homogeneous equation and also to be able to solve this homogeneous equation is really important, because we just do this in 2 steps. Number 1, if you're given any differential equation, something like this in 7, okay, first, instead of the g of x, we just write 0, we just solve this homogeneous part, okay? And after that, we just put g of x here, and we try to find another solution. Actually, the solution, we call this particular solution, okay? One is complementary solution. The solution of this homogeneous equation, we call this um, complementary solution, and when we have g of x here, we find another solution that is particular solution. Okay, so general solution. Let Yp be any particular solution of the non-homogeneous linear nth order differential equation set. Okay, any particular solution on an interval I. We mean that, for example, just one example here, we have y double prime, for example, 4 times y is equal to 16. Okay, if you think about this, what is the order of this differential equation? Second order, right? Is it linear? Yes, right? Because y is not multiplied by any by itself or the derivative of y, right? One solution of this one, for example, particular solution. In the next section of this chapter, we will learn how to solve this homogeneous equation, how to find this particular solution, right? But here just we are trying to understand, we are trying to learn what we mean by particular solution and the complementary solution. Here, as you see here, this is 16, right? For example, if I just write y, one of the particular solution is, what is it? 4, right? Because if you substitute here, if you differentiate this 4 2 times is equal to 0, and 4 times 4 is equal to 16. Okay, as you see here, it looks like to this function, right? Here is a function. Or if I write something like this, for example, let's say, again, y double prime minus 2 times y is equal to, let's say, 2x minus 1, for example. How do you find one particular solution of this equation? I can show you, for example, one particular solution is equal to, what is it? It is minus x plus 1 over 2, right? If you substitute here, if you differentiate twice, is equal to 0, right? And negative 2 times negative x is equal to 2x. Negative 2 times positive half, that's equal to negative 1. Okay, particular solution. Anyway, so what we mean by particular solution is this. Okay, and let y sub 1, y sub 2, dot, 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 y sub n be a fundamental set of solutions. And this thing, again, actually we did this. We are supposed to learn this in the previous video. Of the associated homogeneous differential equation 6 on I. The 6 is that our homogeneous equation. Then the general solution of the equation on the interval is equal to this. What do we see here? We see here this part, right? This part, what is this? Just all the linear combinations of this fundamental set of solutions, right? This y1 and y2, blah, blah, yn. What are these? These are fundamental set of solutions of equation 6, right? And we are just adding particular solution to this. Okay. So that means that, what is it here? We have then y, the general solution will be equal to, we call this complementary solution, y sub c plus y sub p, right? To get this one, actually we need to solve that equation 6. Here we have our equation that's equal to 0. To find this one, that our equation is equal to f of or g of x. In our case, g of x, it is g of x, right? And we just substitute them, their sum, actually, the solution of this equation, the solution of this equation together, it gives us the general solution of the equation in 7. Okay? All right, that complementary solutions, and that we have already talked about this. All right. One example, general solution of a non-homogeneous differential equation. Consider the following: y triple prime minus 6 times y double prime plus 11 times y prime minus 6y equals 3x. Okay, here the coefficients are constant, but it doesn't mean that always they have to be constant. Okay, so it is 3x. But now, in the second part of this chapter, we'll just focus on when the coefficients are constants. Okay, one particular solution, minus 11 over 12 minus 1 over 2x. Okay, and see here y, actually, where do we get this from? This thing, actually, we need to determine this depending on the nature of this. Okay, this function, what kind of function is it? Is a linear function, so also particle solution must be linear function. For example, if we have sine of x, it will be linear combination of sine and cosine. Okay, anyway, we'll talk about this in detail. So here, particle solution is this. If you substitute here, differentiate 3 times is equal to 0, differentiate 2 times is equal to 0, and the differentiate 1 time, if you differentiate 1 time, it is 0, that is minus 1 over 2, right? And here, this one is 0, minus 0, plus 11 times differentiate once. So if you differentiate once, this constant term is equal to 0. This one is negative half, right? And minus 6 times a particular solution, negative 11 over 12 minus 1 over 2x. And if you just simplify this, here we have minus 11 over 2. Here we have minus plus, right? 11 over 2. And it is plus 3x, right? And negative 11 over 2 plus 11 over 2, that's equal to 0. That's equal to 3x. And that's always equal to 3x, or identically equal to 3x, right? Let's see also the solution. And the complementary solution. You see here, the order is 3. That's why here we have 3 linearly independent functions here. Okay, if the order is 2, then usually we'll have 2 functions here. If the order is 1, at that time it's just, what is it? C times something. All right, if you remember, for example, if we have y prime plus y is equal to, let's say, just 0. Okay, and this one is, how many solutions does it have? Only one, right? What is y? Maybe it's something like c to e to the power x, something. Okay, if it's second order, at that time we'll have here one function plus one function. Actually, these functions are linearly independent functions. Okay, so then what will be the solution of this differential equation? The solution of this differential equation will be, it is complementary solution plus particular solution. And complementary solution is this, that is C1 e to the power x plus C2 e to the power 2x plus C3 e to the power 3x plus complementary solution, actually it is minus 11 over 12 minus 1 over 2x. Okay, this is the general solution of the given equation. It's a non-homogeneous equation, right? To do this one, we are doing this in 2 steps. Number 1, first I solve this, and that is equal to 0, and it gives us complementary solution. And after that, this thing is equal to 3x, and it gives us particular solution. And some of these things gives us, what is it? The general solution of this equation. Okay, because if you just substitute here, does it work? Yes, because we know that the differential operator is linear, right? Because of this linearity, right? We can just separate this, get what is the sum of 2 things. Guys, 1 minute. Hello? Good morning. Yes. Uh-huh. Really? Actually, I was waiting for your call, but I was thinking about that. So now I can go and get it. In Novodon Boulevard, right? Today maybe I'm busy. Maybe tomorrow. Tomorrow or Saturday. Is Saturday okay if I come maybe like? Okay, thank you very much. Okay, thank you. Bye bye. Okay. Yehin, are you there?
Yes, sir.
Is everything clear?
Yes, sir. It's clear.
Yeah. Actually, when we just start solving differential equations, all right, it will be more clear because now it's just a theory. In chapter 4.2, we start solving the questions. You will see that always when you're solving differential equation, first we need to solve this homogeneous part, and after that we try to find a particular solution. Okay. Also finding particular solution, it is not so difficult, but it's not a how to say, short procedure. It's quite long, but it is. But we just follow some fixed rules. It's not so complicated. All right, that's the last superposition principle. Non-homogeneous equations. Okay, this is also a very useful theorem and very easy to understand. Let's with y sub p1 and p2 and pk be k particular solutions of the homogeneous linear nth order differential equation set. Okay, we are talking about that equation, and now here we have k particular solutions. All right, it's not fundamental solutions, particular solutions on interval I, corresponding in turn to k distinct functions g1, g2, and gk. Okay, now we are talking about this equation. On the right hand side, the left hand side is not changing. On the right hand side, if it is g1, okay, it is particle solution is this. If it is g sub 2, its particle solution is this. If it is g sub k, for example, it is particle solution is this. Right? Here we have k non-homogeneous equations. The left-hand sides are all the same, but only right-hand sides are different. Right? If I just denote this side with, let's say that equation, right? The first equation, all equations the same. Here we have g1, and here we have the same equation, but here we have g2 dot dot dot, and here we have equation, the same equation is. Here we have g sub k. Okay. So particle solution means if I substitute this in the first equation, it satisfies this equation. It's a solution, particle solution of this equation. If I substitute this here, it's a particle solution of this equation. If I substitute this here, it is a particle solution of this equation. Okay. And it says that then this y sub p, what is it? It's just the sum of all of these particle solutions is a particle solution of this equation. Now again, here we have equation, right? Let's say we are talking about the same equation, left hand side is not changing. On the right hand side, we have the sum of these functions, g sub k, okay? Again, why is it so? We are just using the linearity property of this differential operator, right? And if you remember this differential operator, this L, here we have alpha times f plus beta times g, alpha and beta constant numbers, f and g, two functions of x. So that's equal to alpha times differential operator of f plus beta times differential operator of g. Okay. Now, because if you substitute these things, because these are the solutions, right? And if I substitute here, I can just write one equation in y sub p1 plus the second one y sub p2 and case one in y sub pk, right? And after that, if you just add them, each equation with y sub p1 equals g1, the second one g2 and gk. They're just grouping here. Example, superposition. Verify that this one y sub p1 equals minus 4x squared is a particle solution of this. Can we verify this? We can verify this. I can just verify only one of them. Let's just verify the first one. So here If you verify the first one, minus 4x squared. If you differentiate twice, 2 comes here, negative 8, right? This one is y double prime minus 3y prime plus 4y equals, differentiate this twice, it is negative 8 minus 3 times, differentiate this once, it is negative 8x plus 4 times minus 4x squared, which is equal to negative 8. Here we have plus 24x and minus 16x squared. The same thing, minus 16x squared, 24x minus 8. That means that this thing is one particle solution of this equation. Okay. Similarly, also this one is particle solution of this equation. You can check this, differentiate twice, differentiate once, and substitute here, evaluate, you will get this function. And also this one is the particle solution of this. Okay. So as you see here, left-hand side is not changing. Okay. Now, if I write one equation like this, y double prime minus 3y prime plus 4y. Okay, let me just call this, label this by g sub 1, g sub 2, and g sub 3. Okay. Now, if I form new equation, but here we have g sub 1 plus g sub 2 plus g sub 3. This plus this plus this. Now the question is, what would be the particle solution of this equation? The left-hand side not changing, right? Then particle solution of this equation will be just simply this plus this plus this. That's equal to minus 4x squared plus e to the power 2x plus x times e to the power x. Okay, this one is y sub p1, right? And this one is y sub p2, and this one is y p sub 3. Okay, because if you substitute here again, let me just show one thing here. For example, minus 3y prime, right? And I'm saying that these are the solutions. So that is minus 3. Right here we have, we just write here y sub p1 plus y sub p2 plus y sub p3. And which is equal to, I can just write it as minus 3 y sub p1 minus 3 y sub p2 minus 3 y sub p3, right? Now, here in the similar way, just differentiate this twice, right? The first term, I get this one. The second term, I get this one. The third term, I get this one. And just reorganize this, I will have something like this, but 3, right? Using the first one, you are using the first particle solution. The second equation involving this, the third one involving this. And each one actually corresponds, respectively equal to this thing plus this thing and plus this thing. Okay, and this theorem is all about this. Okay, so guys, I will end this. I will give you a 5-minute break. Okay, because that's all about the first part. Now we will start 4.2. Learn how to solve differential equations. Okay, 5-minute break. After 5 minutes, we'll continue.